Hey there, can folks in the chat hear me? Excellent, thanks. So, as always, don't forget to do the seating survey. And the only assignments for this week are the exam, which is going to be hopefully released tomorrow at 5. Will be due Sunday at 5. I'm giving you an extra day this time so that there's more of an opportunity to get it done before the Thanksgiving break, if that is your desire to do so. And then there's also Piazza participation this week. Do we have any logistical questions before we get started on content? Okay, so there were really only a couple of Piazza questions that have not yet been fully addressed. I wanted to go over those. And then there's a particular kind of question that I went over yesterday that seemed to spawn some good discussion about what we're doing with solubility. And so I thought I would do a similar thing today as well. So first question here, there seems to be some continuing confusion about what is meant by conjugates when we're talking about acids and bases. So let me talk about that a little bit. For any acid-base reaction by the Bronsted-Lowry definition, we have a proton donor and a proton acceptor. So let's say we have HCOOH, which is formic acid, and we write down its standard acid reaction. By standard acid reaction, I mean that it reacts with water and it is acting as an acid, meaning that it is donating a proton. So you look at this chemical formula and you remove an H plus from it. We are left with HCOO minus, aqueous. The water is gaining the proton, so it becomes H3O plus, aqueous. And what we notice is that if we look at the reverse reaction, the water is donating a proton and the formate ion that we have here is accepting that proton. So this, for the forward reaction, is acting as the acid. The water is acting as the base because it is accepting a proton. For the reverse reaction, the formate ion is accepting a proton, and so it is acting as a base, and the hydronium ion is donating a proton, so it is acting as an acid. So the way to think about this is as though you have two species that are basically giving and receiving these protons. This combination, the acid on the left and the base on the right, are essentially the same species, just with or without that proton. And so since it's the same species, we call them a conjugate pair. Similarly, the water and the hydronium are a conjugate pair. So this is important to be able to identify because when we are trying to make a buffer, we need to have an acid and its conjugate base. So in this, if we decided to make a formate based buffer, we would use formic acid and a roughly equal amount of the formate ion that we would get into solution by something like a sodium formate, potassium formate, something like that. It is also useful to identify conjugate pairs because there's a relationship between the Ka of the acid and the Kb of its conjugate base. That relationship is that Ka times Kb equals Kw. And so if you have a table that has a list of Ka values, and yet what you're trying to do is look at what the pH of something like sodium formate would be, noticing that this is going to split off into sodium ions and formate ions, then what you're looking for is the base reaction of the formate ion, HCOO minus aqueous plus H2O is in equilibrium with formic acid, aqueous, plus the hydroxide ion. We can find the Kb for this from the Ka for formic acid. So these are a couple of the reasons why being able to identify conjugate pairs like this is extremely important. Okay, do we have any questions on identifying acids and bases, on identifying conjugate pairs, and what we do with them? Okay. Okay, there's a question about the dissolution stoichiometry of an equilibrium and how that affects the equation used to find molar solubility. And based on a variety of Piazza questions and a variety of questions in my office hours, I'm finding that there seems to be some confusion about the relationship between a KSP, the equilibrium constant for dissolution, and the molar solubility, what exactly their relationship is. So I'd like to go into that in a little bit more detail, and we will get to the specific idea of the dissolution stoichiometry as part of that. So let's take some kind of ionic compound. Let us do calcium phosphate. So calcium has a 2+ charge. Phosphate is PO4 3-. And so if we are going to make this into a neutral compound, we need to have 3 calciums and 2 phosphates. So Ca2, PO4, I'm sorry, Ca3, PO4 2. Now, if we look at the dissolution reaction, so this is a solid, and we are dissolving it, it forms 3 Ca2+ ions, aqueous, and 2 PO4 3- aqueous ions. So if we write down the equilibrium expression for this compound, we call this the KSP, for solubility product. We have the calcium ion concentration to the 3rd power, and we have the phosphate ion concentration squared. Now, if we imagine dissolving this compound in water, and we are starting out without any calcium or phosphate initially dissolved into the water, we do this using an ice table. For this kind of problem, once you get some practice, you might be able to bypass using the ice table. But until you get that kind of familiarity with it, I recommend going with the ice table. We have an initial amount of 0 for both of our compounds, and we're trying to figure out what the how much ends up dissolving. So for every X moles of Ca3PO4 that dissolves, we get 3X calcium plus ions and 2X PO4 3- ions. So 3X, 2X. And so then if we look at our KSP, that is going to be, we have the expression up here, it's going to be 3X, the quantity cubed, and 2X, the quantity squared. Now, a question that came up earlier in the week on this is, is that to some people it feels like we're kind of double counting the stoichiometric coefficients because we're using them both as coefficients in the parentheses here and as the exponent. But they're there for different reasons. Right? Here it is for the stoichiometry because if the reaction proceeds by an amount x, then we have to have 3x of it generated. So that's why we have the coefficient. But then it's also in the exponent because that's how the equilibrium constants work. You take the concentration, whatever it is, and raise it to the third power. So you have to have both of those in place here. So this gets at the KSP and how that's used. If we had an actual value for the KSP here, we could go back and calculate what x is and figure out actually what how much dissolves. But where in all of this is the molar solubility of the substance? Let's think about that. That is, the molar solubility is talking about how much of the starting material dissolves. So molar solubility is the concentration of the starting material as dissolved. So this is if we're looking at the concentration of this is a shorthand. This is not saying that we have units that are dissolved where that unit is 3 calcium ions and 2 phosphate ions stuck together. This is a shorthand for 3 separate calcium ions and 2 separate phosphate ions that are being dissolved. But if we look at the expression that we have here, if we look at this, the amount of calcium phosphate that goes away, if we did include that in our change line, it would be minus a single x, right? Because it has a stoichiometric coefficient of 1. So x is our molar solubility. Right. So a way to tell about this somewhat is to think about it, is let's think about the units. And I know that what I'm about to tell you is going to disagree with how Newton handles this. But I'm not incredibly happy with the way Newton handles this particular issue of units. Newton says that equilibrium constants should be unitless. And there's a sense in which that's true, but you don't get to that sense in which it's true until analytical chemistry or physical chemistry. So at this point, I'm going to say Newton is wrong in this for general chemistry level. And let's look at the units that we have on the KSP up here. If it is a concentration cubed times a concentration squared, our units here are going to be molar to the 5th, right? Here, the molar solubility is just molar, just M. Okay. So there's a question from the chat, just clarifying. Does this mean that X is always the molar solubility? So if we were given X equals 2.4 times 10 to the negative 4th, that's what the molar solubility would be. Okay, so let's think about that. If you are starting with 0 on the right-hand side, and if you have a stoichiometric coefficient of 1 on the left-hand side, then yes, X will be the molar solubility. That's absolutely correct. And if you are comparing this to a KSP, which is generally how you're going to do this, you will always be putting 1 mole on the left-hand side. So it should indeed always be X. Now, there have been a couple of Newton problems I have seen where you start with some of one of the ions already in solution, and then it asks you at that point to calculate the molar solubility of the substance, and it's going to end up being lower than it would be if you didn't already have some ions in solution because of the common ion effect. I have trouble calling that a molar solubility because I think that a molar solubility is really about how much it will dissolve in water when there's nothing else there. I think you could say that's how much will dissolve in this situation, but it's a very specific situation, and I don't like giving it that name. So from my perspective, and certainly from the exam perspective, I would always call if I use the term molar solubility, it will be this situation where you have a stoichiometric coefficient of 1 on the left. You're starting with nothing on the right. And so X will always end up being that molar solubility. So that is the relationship between the solubility product form of an equilibrium constant and the molar solubility. And going a little bit more into where specifically these coefficients play roles, and so the dissolution stoichiometry in particular. Anybody have any clarifying questions about this kind of material, this kind of content? Okay, so one of the things I did yesterday that I think was very useful to go through was I put up a chart that looks like this. This is unfortunately a bad image of it. I apologize for that. I had a printout of it yesterday. I lost the file I used for it, and so just before coming into class, I took a screenshot from the video from yesterday. So I apologize for the poor quality of this. I don't know why nobody presents this information in this way, because it makes so much sense to me to have it like this, where you have combinations of cations and anions, and you have solubility products. These are the KSPs. You have KSPs for each combination that you have. So if you have magnesium chloride, so it would be MgCl2, you have this number for the solubility product for it. The question that spawned me using this kind of chart was someone asking me about what are the periodic trends for solubilities, specifically with things like the halides, metal halides of various kinds. But in general, can we look at the periodic table and come up with some trends about what the solubilities are going to be like? And I honestly didn't know the answer to that question, which is why I put this table together to look at it. And what I found is there aren't any. There are no good trends. So if you look at, say, the fluorides of the alkali metals here, they are generally increasing as you go down here. But then if you look at the 2+ ions with the fluorides, they go down and then back up. Okay, we look at the chlorides. It goes down and then up. It goes up and then down. Okay, the bromides, they seem to go down and then kind of stabilize. Iodides seem to generally kind of go down, but here it goes down and then back up. Here it goes up and then down. If we look across, the fluorides are generally the lowest solubilities across the board, except not for potassium, rubidium, and cesium. So I came to the conclusion that there really aren't any trends. So at least nothing that seems to be particularly reliable. So all of these questions in Newton that are asking you to look at the periodic table and then to predict the solubility of things, I don't think you can do that. I think you actually have to look at data in order to figure that out, figure out what's going on. But then the next thing I did was I took this to explore how we would determine something like in a mixture what would precipitate out, and then how much of it would precipitate out, and how much of the ions would be left after the precipitation happens. So those are kinds of questions that you can ask about complex mixtures of multiple multiple salts. And so that's the very kind of question that I could very easily ask on the exam. So if you guys would like me to, I will go through that kind of thing here as well. Yes? Okay, seeing some nods. Okay, so what I'm going to do is I'm going to pick, let's say potassium fluoride, where we have a KSP of 308, and that's going to be in units of molar squared. And I'm going to pick, let's say, calcium chloride, which has a KSP of 1,210, and that's going to be in, that's going to be molar cubed for our units. Okay. We're going to make solutions of each of these, and we're going to mix the solutions together. And so when we mix the solutions together, we're also going to need to worry about calcium fluoride, the cross product, and potassium chloride, the cross product. So I'm going to put their KSPs down here as well. So potassium chloride has a KSP of 20.8 molar squared, and calcium fluoride has a KSP of 3.9 times 10 to the negative 11 molar cubed. So you may be able to see why I picked these particular examples, because we have 3 cases where we have relatively large KSPs, and we have one that is absolutely tiny. Okay, so this is the setup. So what we're going to do is we are going to make 100 milliliters of a 0.1 molar solution of KF, and we're going to make 100 milliliters of a 0.1 molar solution of calcium chloride. We're going to mix them together, and then we're going to ask what happens. So in situations of this type, and this is true for weak acid or weak base kinds of problems as well when we're doing a titration, when we add a solution to another solution, we have dilution that is happening. And so we have to be able to keep track of the change in concentration due to just dilution. In these kinds of problems, the easiest way to do that is, or the most consistent way to do this, is to keep track of the number of moles that you're dealing with rather than the concentrations. In this particular case, it's going to be relatively easy because if we take 100 mils of this and 100 mils of this, and it's the same volume, so we're basically going to cut each of these concentrations in half. Okay? So we can kind of skip ahead to that answer, but in the general case, if you're not given convenient numbers like this, what you're going to do is calculate the volume times the concentration to get the number of moles. You go through that, find the number of moles, then you divide that by the new total volume that you're going to be working with. But since we have this one as an easy combination, let's go ahead and just write down what the initial concentrations of the ions before we let them react are going to be. So potassium fluoride is going to split into potassium ions and fluoride ions. And so our potassium ion concentration is going to be half of the initial concentration here because it gets diluted. So it's going to be 0.05 molar potassium. Same thing for the fluoride. And I'm going to mark these with an I for initial, 0.05 molar. We can do the same thing with the calcium. Ca2 plus, initial, 0.05 molar. And the chloride, because of the stoichiometry, for every mole of CaCl2 that dissolves, you get 2 moles of chloride ions. So that means that the chloride ion concentration, initial, is going to be 0.1 molar. Okay. So here we go. Can I post a picture of this table somewhere? It's really hard to see over Zoom. Yes, it is difficult to see over Zoom, I agree. I will try to put this table together again and post it so that you can practice with it. Why is it 0.5 and not 0.1 molar? Okay, so we start with 0.1 molar and we mix this solution with this solution. When we do that, we have 200 milliliters, but the 0.1 molar only came from half of it. So it's being diluted by a factor of 2 to 0.05. Okay. All right, so is everybody okay up to this point as to our starting points, starting concentrations? All right. So now we need to see what's going to happen to this. So we know that the potassium fluoride and the calcium chloride already dissolved, so we don't need to do any kind of calculation to prove that potassium fluoride's not going to precipitate and calcium chloride's not going to precipitate, because we know we already made those. So let's do the calculations for both potassium chloride and calcium fluoride. Potassium chloride, let us write down the dissolution reaction. KCl solid is in equilibrium with K plus aqueous and Cl minus aqueous. We have our KSP equals 20.8 molar squared, and that's going to equal the potassium ion concentration at equilibrium times the chloride ion concentration at equilibrium. Now, we are only at equilibrium if there is enough potassium chloride here for there to be some solid precipitate. We don't know if we are at equilibrium yet, so if we multiply the potassium ion concentration by the chloride ion concentration, we are not determining KSP, we are determining Q, the reaction quotient. So Q is of the same form as the equilibrium constant. It's just not necessarily at equilibrium. So in this case, we have 0.1 times 0.05, and we get a Q of 0.005 molar squared. So how does that relate to the KSP? It's significantly smaller than the KSP. And remember, when Q is less than the equilibrium constant, then that means the reaction will shift to the right. Except we don't have any potassium chloride solid, so this is unsaturated. There will be no potassium chloride precipitate. Anybody have any questions about that conclusion? Okay. Let's now take a look at the calcium fluoride example. So, we still need the data here. So, calcium fluoride, in equilibrium with Ca2 plus aqueous plus 2 F minus aqueous. We have our KSP is, let's get the number, 3.9 times 10 to the negative 11th molar cubed. And our expression for this is Ca2 plus concentration times the F minus concentration squared. So if we look at our initial concentrations, so we can get our Q, so these are at EQ. If we look at our Q, our calcium ion concentration is 0.05 molar. Our fluoride ion concentration is the same thing, 0.05 molar squared. So it's going to be 0.05 cubed. So 0.05 cubed is 1.25 times 10 to the negative 4 molar cubed. So our Q is significantly larger than our KSP. So when Q is greater than KSP, then the equilibrium, the reaction shifts to the left, and so we do in fact get a precipitate. The next questions we can ask then are how much precipitate do we get and how much of the ions remain in solution. So to figure out those questions, we use an ice table. So CaF2 solid in equilibrium with Ca2 plus aqueous plus 2F minus aqueous. We know that we are starting with 0.05 molar calcium and 0.05 molar fluoride. Now, we suspect, based on how tiny the equilibrium constant is, that there's probably not going to be much of this left in solution. So it makes sense to shift the equilibrium as far to the left as possible so that we're starting close to equilibrium, and then let it correct back with the x's in the change line. So let's do that. So we start with the same amount of calcium and fluoride, but during the precipitation reaction, we use up the fluoride twice as fast as we use up the calcium. So the fluoride's going to run out first, so our shifted initial is going to be 0. But we're going to use up half of the calcium. So this is going to become 0.025 molar of the calcium for our shifted initial. I know that the shifted initial conditions line has caused some confusion in the past. Does anybody need any further explanation for that? When do you know when to use shifted initial? Well, when you think that you are starting off a long way away from equilibrium, that's when you should do a shifted initial conditions. Because what happens when you do the shifted initial conditions is that in this case, we're going to end up with just an x in this place. And we're going to have 0.025 plus an x kind of thing in this place. And so we might be able to ignore this x, and so our math becomes easier when there's a 0 that we're adding x's to. So that's the general idea. So now if we look at our change line from our shifted initial, it has to be shifting to the right because we're starting with 0 fluoride under these shifted initial conditions. So for every mole of, for every X amount of calcium fluoride that dissolves, we get X calcium and 2X fluoride. 0.025 plus X, 2X. And we will assume that we can neglect that x to make the math easier, and we will double check that answer in a moment. We now take our KSP expression, 3.9 times 10 to the negative 11th molar cubed, which equals our calcium ion concentration, 0.025 molar, times 2x squared. X squared is going to be 3.9 times 10 to the negative 11th molar cubed over 0.025 molar. 2 squared is 4. So we can find out what that is. 3.9 times 10 to the negative 11th divided by 0.025 divided by 4, and we get 3.9 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molar squared. Take the square root of that. We have 1.97 times 10 to the negative 1, 2, 3, 4, 5 molar. And we see that indeed this is small compared to the 0.025. So our assumption that we can neglect it here is validated. So now that we know our equilibrium position, we can answer several questions. How much calcium fluoride precipitated? Well, since the amount that is still in solution is negligible compared to the amount that, that was precipitated, all we have to do is find out how much precipitated. So we look at all of the fluoride concentration. So we have, where are we here? So the amount of fluoride we started with was this. So we have 200 mils of 0.05 moles of fluoride in 1 liter. So that's the molarity. 1,000 mils over, nope, other way around. 1 liter, 1,000 mils. And so that's going to tell us how many moles of fluoride ion we have. And for every 2 moles of fluoride ion, we have 1 mole of calcium fluoride that's formed. And so 200 times 0.05 divided by 1,000 divided by 2 gives us 0.005 moles of calcium fluoride. And if you wanted to convert that into grams, you could, just by using the molar mass of calcium fluoride. How much calcium remains in solution? Well, 0.025. How much fluoride remains in solution? 2x. So if we call this, if 1.97, we weren't really tracking sig figs in this, but call it 2 times 10 to the negative 5, so it's going to be 4 times 10 to the negative 5 molar fluoride. It's going to be what's left in solution. And the other 2 ions, the chlorine and the potassium, are unchanged from their initial states because they did not participate in anything that precipitated. So this is the general idea of about how to think about a case where you have multiple ions floating around that can be interacting with each other. So one thing I didn't really emphasize here, but is probably worth mentioning, is that when we set up this problem, we said we had a solution of potassium fluoride and a solution of calcium chloride, and we mixed them together. When we do that, we should no longer think of the potassium fluoride as being associated with each other, and we should no longer think of the calcium chloride as being associated with each other. Instead, we have a single solution that has some K plus in it, that has some F minus in it, that has some Ca2 plus in it, and that has some Cl minus in it. And we actually have twice as much Cl minus. And so all of these are floating around independently, and all of them can run into each other. And so what you do then is you just look at all the combinations that you could get to see what, are there any combinations where something will happen? In this case, nothing happens. In this case, nothing happens. In this case, nothing happens. It is only in this case where something ends up happening. Okay, any questions on this kind of material? Okay, I am happy to try to address anything else anybody would like me to talk about. Coupled equilibria and Le Chatelier's principle, using the common ion effect. There's all the stuff with buffers and titrations. How would I state that question on the test? Meaning the one I just went through? So probably what I would do is give you a set of solubility constants, solubility products, or molar solubilities. I would tell you that certain things are being mixed, and then I would ask you to determine which species are going to precipitate, if any, and then ask you how much precipitates, how much is left of the various species. I might give you questions along the way to that. So if I gave you molar solubilities, I would probably then ask you as an earlier question to calculate the KSPs so that you know to do that step. And then from the KSPs, I would then ask you a question about after you mix the two samples, what would the initial concentrations be before you allow things to precipitate? Then ask you which ones precipitate, which ones don't, and then the amounts, something like that. An alternate way to do this kind of thing would be to give you a larger table sort of like this that has a bunch of different solubility products or molar solubilities, and then tell you that you have this particular ion in solution. So maybe you have, let's say you have the cesium. No, that's not a good one to pick. Let's say you have the lithium ion in solution, and you want to get as much of it out as possible. And so the question then would be, what would you do in order to get it out? And so what you do here is you look across and you see, well, the fluoride ion is the one that has by far the lowest solubility product. So if I put in some fluoride, then I'm likely to be able to pull out the lithium fluoride. And then you could then build onto that by asking, if you're trying to get rid of the lithium, but you're not trying to get rid of maybe the sodium, then you could do a calculation about how much how much fluoride would you add, how much lithium would come out, and would the sodium stay in solution or not under those conditions. So question here, if we would calculate KSP, then how do we calculate Q and know the difference to decide which way the shift is? So calculating the KSP would be calculating it from the molar solubility in the scenario I just described. So you would have the molar solubility and would calculate KSP from that. And then once you have the KSP, you would have to have what your conditions are to be able to calculate the Q. Does that make sense? I'm not sure. All right, is there anything else we can talk about? What other material would you like me to go into? So a question here, asking for a refresher on the reaction quotient, about which way K shifts. So, sorry, Q greater than K, Q equal K, and Q less than K. So the thing to remember about in all of these cases, instead of trying to memorize what each of these do, I like to think of it in terms of the numerator. So remember that both of these, the Q and the K, is products over reactants. So if Q is bigger than K, then that means the numerator is too big, which means that products are going to turn into reactants. The reaction will shift away from products towards reactants. If Q is less than K, then that means your numerator is too small. You don't have enough products, so reactants are going to have to convert into products. So that way, just remembering products over reactants tells you all of these facts right here about what happens based on Q. So that's one thing to remember instead of three things to remember. Okay. Students are still a bit shaky on how to do titrations. I agree, that's a little bit tough. So I did post a video that walks through the calculations in the different regimes that you're operating in on a titration. So the example is usually a weak acid, strong base example. And so generally you have a region here around the buffer point. So we have our equivalence point here. Which can be determined very precisely in terms of volume because it's so steep at that point. If it's a weak acid, then we end up with a pH above 7 at the equivalence point. The half equivalence point, so half of the volume, is going to be the center of the buffer region. So this is the point here where concentration of HA equals concentration of A minus. And so in the Henderson-Hasselbalch equation, pH equals pKa plus log base 10 of A minus over HA. And so when this ratio of the concentration of A minus and the concentration of HA is anywhere from 9 to 1 to 1 to 9 in that range, then the Henderson-Hasselbalch equation gives you very accurate results. And so, and that is a lot faster than doing a full ice table. If you're outside this range, so down in here, and then between here and pH 7, then you really need to do an ice table for the acid reaction. Between 7 and the equivalence point, you need to do an ice table for the conjugate base reaction. Above the equivalence point, all you need to know is how much excess base. So the way to think about this is that we have our acid, so HA plus H2O is in equilibrium with A minus plus H3O plus. At the start of the titration, we just have the HA. As we add base to it, what we are doing is yanking off hydrogens from the acid and making the base. And so the values that we put into the Henderson-Hasselbalch equation are simply how much acid do you have? So you have your HA initial minus the OH minus added gives us the HA that we're going to be using. And then the OH minus added gives us the A minus that we're going to use in this calculation. At least up until the point, at least up until the equivalence point. Because at the equivalence point, all of it has been turned into A minus. And so after that point, then you just look at how much excess OH minus there is. So the OH minus added is going to be larger than the HA you started with. So OH minus minus the initial HA gives you the OH minus final. And so you find the POH and subtract it from 14 to get the pH. So I go through calculations in each of these regimes in that video that I posted. So I do recommend taking a look at that one. What you might want to think about is what would this look like in reverse? So if we were using a weak base and we're titrating it with a strong acid, how is this going to look? So the other complication is dealing with polyprotic acids. And so we talked in some of the class periods about what the titration curve looks like for phosphoric acid. And I think there's actually a phosphoric acid titration you do in the PChem lab, not PChem lab, in the Gen Chem lab. And so you have seen that kind of thing before as well. I did take a look at the post-lab questions for the titrations that you've done in the labs, and those are actually really good kinds of questions. So if you're wondering the kinds of things that could be on the exam, those give you a pretty good idea of the kinds of things that I could ask about titrations on the exam. So there's a question in the chat saying, other example problems that are going to be like the test. So certainly there's going to be something having to do with precipitation reactions like we went through early on. There's going to be some things about titrations with calculations that are involved in it to find pH at different points in that. There's going to have to be some things on buffers. I like to use sort of real world examples for the buffers, and since we already did blood, I'm thinking of trying to do something different. So I don't know if I'm going to do this one or not, but I'm contemplating something like the buffering capacity of the oceans that that you have. So because the oceans have dissolved carbon dioxide, it still has the carbonate, bicarbonate kind of buffer system that was the same one that you used in blood. But of course, the amounts are going to be somewhat different in those cases. I don't know, I may find some other type of natural buffer system to look at. I'm still writing that portion of the test. Then there's almost certainly going to be something on coupled equilibria where you have common ion effects going on and trying to determine how when you perturb a coupled equilibrium system in some way, what the effects will be on other parts of the system. That's most of it. There's a lot of acid-base stuff. I mean, we spent 2 full weeks on the acid-base things. Maybe something on relative strengths of acids using periodic trends on those. So you may remember we went through those examples for looking at oxidation number of central atoms in the in like sulfate versus sulfuric acid versus sulfurous acid, and there are certainly a number of other examples of that same type that we could do. There may be a question on Lewis acid-based kinds of things, but I'm not going to emphasize that very much. I wouldn't think I would do more than one question on that, simply because we haven't done a lot with it. I mostly wanted you guys to be exposed to that rather than go into major depth with that. That's about all I can think of in terms of content. Does anybody else remember any content that we went over the last 3 weeks that I didn't mention there? No? Okay. I might ask you a little bit about how a change in temperature might affect how you would think about pH and pOH, since Kw is going to change under those conditions. So that would be getting at the kinds of issues of understanding why we say that pH plus pOH equals 14, and how to go from Ka to Kb for conjugates. So that would be a kind of thing I might imagine doing. Okay, well, if nobody has any other questions, I'm happy to quit a little early. All right, thank you very much.